In section 5, we're going to begin discussing the reactivity of acids and bases. There are 3 basic reactions that we're going to discuss: acids with metals, acids with carbonates, and acids with bases. We've actually seen several of these reactions in the laboratory, so I might refer back to those. So when we react a metal with an acid, for instance sodium or magnesium or iron, you're going to have a similar product every single time. You might think of this as generally a single replacement reaction, where the metal comes in and pushes the hydrogen out. So now we have hydrogen all by itself because it got pushed out. And the K is now with the anion, with chlorine. Notice it says salt under KCl. Salt is a generic term. We might generally refer to salt as sodium chloride as table salt, but that's a very specific type of salt. Salt in general means any kind of ionic compound. Many people don't realize that. So if we look at zinc at another example, zinc comes in and it pushes hydrogen out. And zinc is now with chlorine. Notice this little 2 here. Zinc is a +2, chlorine's a -1. Crisscross it, and that's how those numbers got there. Notice that there's only a 1 here originally. That's because hydrogen's a +1. These little numbers at the bottom come from the charges. The only exception is if it's a polyatomic ion. Also notice that hydrogen is an H2. That's because it's a diatomic molecule. That means when it's all by itself, there's going to be 2 of them. It's not just going to be singular. Whereas if you look at the metal, there's only 1 potassium. There's only 1 zinc. That's because those are not diatomic molecules. So let's have a practice on our own. We're mixing magnesium with HCl. So magnesium with HCl. Magnesium comes in and pushes hydrogen out. So we have hydrogen gas on the right hand side. Notice that it's at 2 because it's a diatomic molecule. Magnesium is now with the chlorine. If we look on the periodic table, magnesium is here. It's in a row that has a +2 charge. Chlorine is here. It's in a row with a -1 charge. So we crisscross it to have Mg1Cl2. So our final answer is magnesium plus hydrochloric acid yields hydrogen and magnesium chloride. Balance it, and we're done with this one. To label it, magnesium is the metal, hydrochloric acid is the acid, and magnesium chloride is the salt. We've done a few of these reactions in lab itself, where we've put a piece of metal like calcium in an acid solution, and then we watched it fizz out. That fizz that we saw was a hydrogen gas. And here's our answer again. Now we're going to talk about how acids react with carbonates and hydrogen carbonates. So here's our carbonate, CO3. Bicarbonate is HCO3. This is very similar to a double replacement reaction, where the outsides come together and the insides come together. So calcium is now with chlorine. And here we see it right here. Once again, it's called a salt because any ionic compound is considered a salt. Notice this little 2 down here. Once again, if we look at the periodic table, calcium is here. It's in the +2 row. That's where that +2 came from. Chlorine is in the -1 row. So when we crisscross, Ca1, Cl2. Now, the outsides come together to produce H2CO3. But what happens here is that breaks down further and decomposes into carbon dioxide and water. So here's your carbon dioxide, and here's your water. We've actually seen this in lab as well when we mixed vinegar with salt, vinegar and baking soda. That's what we saw that was fizzing out. That's the carbon dioxide. Once again, insides come together, outsides come together. Here's our sodium chloride. Na is a +1, Cl is a -1, which is why we have 1 and 1 down here. And then the outside came together to be H2CO3, which then broke down further into H2O and CO2. CO2 and H2O. So if we practice with this one, insides and outsides, magnesium is now with bromine. Mg is with Br. Once I write down those letters, I have to immediately look at the periodic table. Magnesium is here. It's in the +2 row. Bromine is here. It's in the -1 row. So that becomes MgBr2. The insides become H2CO3, which then become H2O and CO2. From here, you just balance. Insides come together, outsides come together. Insides are Na and Cl. Na is right here, it's a +1, and Cl is right here, it's a -1. So when we crisscross, it's just 1 and 1. And then the outsides, once again, become H2CO3, which then break down into H2O and CO2. So a carbonate with an acid. Here's our salt. Notice the 2 there from the +2 for magnesium. Carbon dioxide and water. Acid with the bicarbonate. Generic name for salt. +1, -1, there's no numbers down here. CO2 and H2O. Notice that CO2 is a gas. H2O is in liquid form. This is what bubbles off when we are mixing things together. And then the salt is actually dissolved in water. Our final reaction is going to be a neutralization reaction. That's when you mix an acid and a base together. Once again, we're going to act as though this is a double replacement reaction, where the inside ones come together and the outside ones come together. So the inside ions are Na and Cl, +1, -1. And then the outside is H2O. When you have a neutralization reaction, what's going to happen is you're going to have a salt, which once again is just an ionic compound, and water every single time. That's the characteristic of a neutralization reaction, is that you're going to end up producing salt and water. The acids and bases cancel each other out. We could, if we wanted to, write this as an aqueous compound and primarily focus on the water. So here's an HCl right here. Here's NaOH. Both of them are dissolved in water. What it's saying is these two aren't really going to do much, but the H and the OH are going to come together for water. Whereas the Na and the Cl are still just sitting there. So since they don't really do anything, we can leave those out of the equation and just focus on the H and the OH to form water. When we're balancing them, you're going to balance them just like we have in the past. So if we're looking at it, we have one hydrogen on the, we have 1 plus 3 more here, so we have 4 hydrogens total. Since I have them in 2 different places, I'm going to save it till the end. So I'm going to go to the next one. Chlorine. There's 3 chlorines on the right hand side, so I'm going to multiply this by 3. Aluminum, 1 and 1. Oxygen, 3. And I'm going to need 3 over here then. So that means I have 6 here. I have 3 hydrogen here, but I have 3 more here. So I have 6 on this side as well. So it's going to be 3, 1, 1, 3, which is C. Go to the next one. Notice PO4 is a polyatomic ion, so I'm going to immediately put that in parentheses because I see it on both the left and the right hand side. Alright, so let's start from left to right. We have barium, we have 1 there, we have 3 here. So I'm going to multiply that by 3 on the left hand side. Oxygens, I have 2 here, and I have that multiplied by 3. So that means I have 6 total. That means I want 6 over here. If we look at the hydrogens, I have 12 here. But I notice on the right hand side I have it in 2 different places. I have 6 here and I have 3 here. So because I have it in 2 different places, I'm going to actually save that one till the end. I don't want to jump the gun. Let's go to the phosphates. We have 1 here. We have 2 of them here, so I'm going to multiply this one by 2. Now I'm going to go back and do the hydrogens. So I have 6 here still. 2 here times 3. I have 6. And I have 6 here. Here's 12. So we're good. So it's going to be 3, 2, 1, 6, which is B. Notice by waiting till the hydrogens till the end, because I saw it in 2 different compounds on one side of the arrow, it kind of worked out on its own and made my life easier. So we're going to write some neutralization reactions on our own. Stomach acid is hydrochloric acid. And it contains, if we use Mylanta to help our acidic stomach, to help our stomach not be so acidy, we're using these 2 compounds. So we can do reactions with HCl and those 2 compounds. So HCl with AlOH3, the insides come together and the outsides come together. Al and Cl are together, and HOH are together. Now if I look at the periodic table, I find that Al is right here. It has a +3. Chlorine is right here. It has a -1. So it becomes Al1Cl3 when we crisscross. And HOH becomes H2O. So it's HCl plus AlOH3 yields AlCl3 and H2O. From here we need to balance. So I'm going to keep H to the end because I see it in 2 different formulas on the left hand side. So now we're going to go to chlorine. We have 1 chlorine on the left, 3 on the right. So I'm going to multiply the left hand side by 3. Now aluminums. We have 1 on the left and 1 on the right, so we're okay. Oxygens. We have 3 on the left and only 1 on the right. So I'm going to multiply the water by 3. Now let's go back and take a look at the hydrogens. We have 6 here, 3 times 2. And we have 3 here and 3 here. So there's 6 there as well. Now we're going to mix HCl with MgOH2. insides come together and the outsides come together. So Mg is now with Cl. Mg is right here on the periodic table, which means it has a +2 charge. Chlorine still has a -1, so that gives us MgCl2. And water. HOH is water. So from here, once again, we're going to balance. Notice I have hydrogen in 2 different places on the left-hand side. So I'm going to ignore that for now and go to the chlorines. I have 1 chlorine on the left, I have 2 on the right. So I'm going to multiply the HCl by 2. Magnesium, 1 and 1, so we're okay. Oxygens, we have 2 here, because this gets multiplied by 2. So that means I need to multiply that by 2 on the right-hand side. That means I now have 4 hydrogens on the right. I have 2 here and 2 here, so that's 4. So we're good. Now let's look at acid-base titrations. A titration is just a laboratory procedure in order to figure out the exact concentration of an acid. We have this extremely accurate piece of equipment right here. That's called a burette. And you fill it up with some basic solution where you know the exact concentration. And then down here we have an acid solution where you have no idea what the concentration is. However, you do know how much you put in there. So you could have measured out 50 milliliters or 50.0 milliliters depending on how much you use and how much you need. And then you determine how much of this got added to it. So you know the exact molarity, and then you know the exact volume. And as we know, molarity is moles over liters. So if we know the volume and we know the molarity, we can figure out how many moles of solution we used. And from there, we can put it into stoichiometry. To determine what's in there. There's an indicator. You can see a slight shade of pink. Phenolphthalein is a common indicator for acid-base reactions because it turns colored at a pH of 7. So we know the exact time when it turns, it's going to be completely neutral. There's going to be, the solution would be more, it would switch over from acidic to basic. An indicator in general will change colors in a solution, so that way we know when it's neutralized. And then the endpoint is when it changes and it doesn't change back. It gives a permanent color. Phenolphthalein specifically turns a pink color. Then we figure out exactly how much of the base in the burette that we used. And then from there we can do calculations to figure out how much the acid is. And we're going to do a practice calculation with that. What is the molarity of HCl? So we're looking for the molarity of this. If 18.75 milliliters of the NaOH, 18.5 milliliters of the NaOH, which is 0.225 molar, are required to neutralize 10.0 milliliters of HCl. Notice they give us information, all the information we need about NaOH, but they're asking about HCl. Because of that, we're changing compounds. That means we need to get into moles. From our solutions chapter, we know that molarity is equal to moles over liters. So if we look at the NaOH specifically, we know that 0.225 molar is equal to X over 0.0185 liters when you divide it by 1,000. So in order to solve for X, you cross multiply. So 0.225 times 0.0185. That means we have 0.00416 moles of NaOH. From here, we can go from moles of one to moles of the other using the coefficients. So 0.00416 moles NaOH over 1. Coefficient of NaOH is 1, so 1 mole NaOH. Coefficient of HCl is 1 mole HCl. So that means we have 0.00416 times 1 divided by 1. That means we have 0.00416 moles of HCl. We're looking for the molarity. So once again, we're looking for the moles over liters. We have the volume right here. So molarity is equal to 0.00416 moles HCl over, we're going to change this milliliters to liters by dividing by 1,000. .01 liters. That then equals 0.416 molar HCl. And that would be our final answer. So as a review, in order to solve a titration reaction calculation, first thing we want to do is figure out the molarity of what we were given. Figure out how many moles we have there. And we did that by using the molarity equation and cross multiplying. From there, we use the coefficients. And then once we figure out how many moles of the acid we had, we divided it by the exact volume of the acid in liters. Make sure that your volume is always in liters. Alright, so let's try another one. Calculate the milliliters of H2SO4. So if we have a 2.00 molar H2SO4 required to neutralize 50 milliliters of 1.00 molar KOH. Once again, once you have your information written out, notice that we're given milliliters and molarity of the KOH. We're looking for the milliliters of H2SO4. We see we have molarity. Molarity is moles over liters. We can figure out how many moles we have, because in order to go from one compound to another compound, you need it in moles. We can figure out how many moles we have by plugging in this information. So 1.00 molar is equal to X over 0.0500 liters. So X is then equal to 0.0500 moles of KOH. Now that we have it in the moles of KOH, we can get it to moles of H2SO4 by using the coefficients. So 0.0500 moles KOH We have moles of KOH on the bottom. Where we're coming from is on the bottom. And that's 2. Where we're going to goes on top. So 1 mole H2SO4. So we're going to divide this number by 2. That comes out to be 0.0250 moles of H2SO4. Now we have the moles and we have the molarity. We want to know how much volume we need. So once again, we're going to use the molarity equation because we know what the molarity is. So 2.00 is equal to 0.0250 over x. Now this is going to be a bit tricky because of the fact that the x is on the bottom. If we put this over 1, we can cross multiply. So that becomes 2.00x is equal to 0.0250. And then from here, we can divide. X is then equal to 0.0125. Now remember, that is actually in liters. We want the answer in milliliters. So in 1 liter, there's 1,000 milliliters. Liters are canceled, so you multiply by 1,000, and that becomes 12.5 milliliters. Now to review what we did, we're looking for the milliliters of this molarity, which we see the M, that automatically means we're going to be using moles over liters. So there's our information for this one. To neutralize 50 milliliters of 1.0 molar solution, we have our information right here. Once again, molarity, moles over liters. In order to get from the KOH over to the H2SO4, we need to use coefficients. In order to use coefficients, we need to get it into moles. So we need to get this top number here. So that's what we did here. We solved for moles on the top by cross multiplying, and that gave us her moles. Once we got it in moles of KOH, we were able to use that with the coefficients, which are right here, to get it into moles of H2SO4. And then we're going to turn around and plug that back into the molarity equation again, and that's going to be our top number. That's what we did here. And it's 2.00 molar. So it's 2.00 is equal to 0.0250 over x. Solve for x, multiply it by 1,000, and that gave us our answer. The math of these can get a little complicated, so take your time and do a lot of practice.